There are moments in science when the world seems to pause, when an observation, a pattern, a single unexpected shape forces every equation we trust to hesitate, as if the universe itself is whispering something it never meant for us to hear. This story begins with such a moment, a discovery so strange, so fundamentally out of place, that its very existence challenges the assumptions that anchor modern cosmology. It began far from the places where discoveries usually happen. Not in a laboratory lined with cooled metal instruments, not in a mountaintop observatory under crystal nights, not even in the data streams from a single mission. Instead, the first hint of the anomaly arrived quietly, buried in a routine recalibration of cosmic microwave background maps, those faint, ancient photons that have been traveling toward us for nearly 14 billion years, the relic light from the beginning of time. At first, it was dismissed as noise, a calibration artifact, a statistical smear created when different sky surveys from different years were stitched together. Scientists are trained to be skeptical, to assume error before miracle. Yet something in this data refused to go away. When the maps were reprocessed with stricter filters, the pattern sharpened. When new noise models were applied, it grew clearer still. And when independent teams working in different labs with different software on different continents reported the same anomaly, the scientific world could no longer look away. It was a structure, not a structure in the sense we know: no stone, no metal, no ancient architecture left by forgotten hands. This was older than any civilization, older than Earth, older than the stars that light our galaxy. It was a structure in the fabric of space itself, a geometry. Imagine looking at the afterglow of the Big Bang and noticing that somewhere, stitched faintly into that vast cosmic quilt, is a shape, a pattern of temperature and polarization variations arranged in a way that should be impossible after cosmic inflation. Inflation, the great smoothing, the unimaginable burst of expansion that erased all irregularities in the first fraction of a second. By all logic, by every cosmological model we trust, no pattern this coherent should have survived that event. It would be like finding intricate calligraphy preserved on the surface of water after a tidal wave has passed. And yet there it was, a faint ring-like symmetry spanning a region thousands of light-years across. Not perfectly circular, but subtly warped, as though distorted by the curvature of a larger geometry beneath it. A ripple that did not behave like noise, or cosmic variance, or the usual statistical bumps that appear in sky surveys. This one had intent, structure, a stability that refused to be averaged away. For months, the anomaly lived quietly in preprint papers and internal emails, nobody wanting to claim too much, nobody willing to ignore what the data showed. Was it natural? Could it be some quirk of early universe physics that we had simply never imagined? Was it accidental? A byproduct of some process happening long before atoms existed, some leftover scaffold from the earliest moments of reality? Or was it the remnant of something even stranger, a trace left behind by a previous cosmic cycle, a universe before ours? The questions piled faster than the answers. The first hypothesis was that it might be a topological defect, a kind of wrinkle created when the universe cooled from its earliest high-energy state. Cosmic strings, domain walls, textures, exotic entities predicted by theoretical physics but never convincingly observed. But even these ideas faltered. The geometry was too organized, too coherent, lacking the random, jagged edges typical of such defects. Another idea suggested gravitational lensing, that some colossal, invisible mass between us and the early universe was bending the ancient light into a symmetrical pattern. Yet there was no sign of the required mass. No cluster, no dark matter halo, no black hole of sufficient scale hiding in the region. In fact, the region was surprisingly empty, and that emptiness made the structure even stranger. It was as if the pattern wasn't caused by something in the universe, but woven into the universe. Days turned into weeks, weeks into months. The JWST team joined the effort, pointing its instruments toward galaxies in the vicinity of the anomaly, hoping their ages or distributions might offer clues. Instead, their observations added another layer of impossibility. The galaxies nearest the anomalous region appeared too evolved for their distance, as though time itself had behaved differently there. Their stars were older than they should have been, their structures more mature. The universe, in that patch of sky, had aged unevenly. By the time the results were presented quietly at a closed conference in mid-2025, the term ancient structure had already begun circulating among the researchers. Not because it was ancient, like a fossil or relic, but because whatever it was had formed before almost anything else in the cosmos, before stars, before galaxies, before the primordial plasma cooled. It seemed to be a scar left on space-time, etched into the universe during its birth, or before it. The idea surfaced reluctantly, almost sheepishly. At first, whispered only in hallways and late-night discussions. What if this shape is not just older than stars, but older than our universe? What if it is pre-cosmic, an inheritance from a cycle of existence that came before the Big Bang? The concept isn't new. Some cosmological models suggest that universes might rise and fall in endless succession, the end of one becoming, in a sense, the beginning of another. But these are mathematical luxuries, abstractions that comfort theorists but rarely leave fingerprints on observable reality. If this structure truly predates the Big Bang, it would be the first direct evidence of a universe before ours. And yet, every time the data was re-examined, the shape remained calm, silent, indifferent to our confusion. A geometry carved not by matter, but by the curvature of space-time itself. An ancient ripple frozen into the universe, like the preserved rings of a tree older than time. It shouldn't exist, but it does, and so the mystery began. A structure not built, not formed, not assembled, simply present. A whisper from the universe's opening act. A pattern untouched by inflation, impervious to chaos, older than the stars, older than time as we understand it. Where did it come from? What shaped it? Why did it survive? Is it natural? A cosmic accident that defied probability? A remnant of a previous cosmos, echoing across cycles of creation and destruction? Or is it something else entirely? The universe rarely offers such questions, and when it does, it rarely offers answers. Yet buried beneath this impossible structure, beneath its quiet defiance of known physics, is a story that stretches across epochs, across dimensions, across the very boundary of existence. To understand it, we must go deeper. We must examine not just the structure itself, but the age of the universe, and whether the universe is as young as we think. When scientists first confronted the anomaly, this silent geometric imprint older than galaxies, the immediate instinct was to look backward, to retrace the history of time itself. The universe, as we understand it, has a timeline as precise as a clock, 13.8 billion years. That is the age engraved into cosmology textbooks, NASA briefings, documentaries, and the worldview of nearly every physicist alive. It is the age derived from the cooling of the cosmic microwave background, from the expansion rate of space, from the life cycles of the oldest stars. It is a number we recite with almost religious certainty. Yet the ancient structure whispered something different, something disobedient, a shape that should have been erased by inflation, that should not have survived the universe's first moments, was still here, calm, symmetrical, waiting. And for the first time in decades, cosmologists were forced to ask a question that once seemed unthinkable. What if the universe is older than we think? or more unsettling what-if age on cosmic scales doesn't work the way we imagine at all. The first cracks in our understanding didn't actually appear with the structure. They appeared elsewhere, quietly, in data collected, years earlier data most scientists hadn't fully appreciated until now. Some of the earliest galaxies observed by JWST in 2023 and 2024 seemed impossibly mature. Their stars were too old, their structures too organized, their chemical elements too enriched. For a brief moment, cosmology was shaken by headlines claiming the universe might be twice as old as believed. The claim wasn't accurate, but it wasn't meaningless either. Those galaxies truly were older than theory allowed at those distances. Something, somewhere, wasn't aligning. Then, in 2024, a new set of inflation models began circulating, a refinement of eternal inflation, suggesting something even stranger, that regions of space-time might undergo inflation at different rates, creating quasi-eternal pockets where time flows unevenly, where expansion accelerates or stabilizes in ways that could make certain regions appear older or younger relative to others. These pockets could preserve structures or allow them to form before the main universe fully emerged, a kind of pre-temporal cradle. The idea was speculative but elegant. It offered a framework in which the geometry discovered in the cosmic microwave background might not be impossible, just older than the universe surrounding it. A pocket of space-time that somehow endured the transition into our cosmic epoch. A relic from the pre-inflationary state. But this raised another question, one that stretched imagination to its limits. How could anything predate the Big Bang? Isn't the Big Bang the beginning of everything? Time, space, physics, existence itself? Not exactly. Not anymore. Modern cosmology no longer imagines the Big Bang as a singular explosion, but as a transformation, an emergence of dense, hot space-time from a previous state. That previous state may not have been time as we understand it, but it wasn't nothing. Quantum gravity models suggest that before inflation began, the universe existed in a primordial foam, chaotic, turbulent, flickering between states. In such an environment, topological structures could form, knots or ridges in space-time, with no matter, no atoms, no particles, pure geometry. Most of these structures would dissolve during inflation. They would stretch, smooth out, or vanish entirely. But if a quasi-eternal pocket existed, an area where inflation behaved differently, the structure might survive. It might be sheltered, preserved, protected from the great smoothing. And if that pocket later merged with the expanding universe we inhabit, its ancient geometry could be carried forward into our cosmic epoch like a fossil from a world that no longer exists. This was the beginning of a radical possibility, that the structure wasn't older than the Big Bang, but older than the conditions that led to the Big Bang. A relic of a pre-inflationary geometry trapped within the fabric of the universe. Still, even that explanation strained the imagination. The structure was too coherent, too mathematical, the edges too softly deliberate. It did not resemble the chaotic, foamy turbulence predicted before inflation. It resembled something sculpted, something shaped by slow evolution over immense time, far more time than the pre-inflationary epoch allows. So researchers widened their scope, turning toward theories once considered fringe: cyclic cosmology, conformal cosmology, universes that oscillate, universes that collapse and rebound, universes that shed information into the next generation. New studies from 2025 revived interest in these ideas, especially after the discovery of low-variance circular patches in reanalyzed CMB data, subtle hints that something from before might still be echoing across the sky. One idea gained traction: pre-Big Bang relics, objects or patterns formed in a previous universe that somehow survived the transition into ours. Unlike matter, unlike energy, Unlike anything with a physical form, these relics would be pure geometry, immune to destruction, indifferent to entropy, carried across cosmic cycles like imprints pressed into clay. In this view, the ancient structure is not an object at all. It is a memory, a leftover, a signature of a universe long gone. A universe with its own physics, its own ages, its own cosmic story that ended before ours began. How could such a relic pass from one universe to the next without violating physics? The key lies in something subtle. Certain properties of space-time are conformal, meaning they can survive extreme transformations. Just as shadows retain shape even when stretched or compressed, conformal structures might survive the collapse of one universe and persist into the next. They wouldn't carry energy, they wouldn't carry matter. They would carry shape, and that shape is what we found. A geometry imprinted onto our universe at birth. The implications are staggering. It suggests that the Big Bang wasn't the beginning of everything, only the beginning of our chapter. It suggests that time may not be a straight line, but a tapestry woven from cycles, transitions, and inheritances. It suggests that age, at the cosmic scale, is not a simple number, but a layered history. So the timeline of the universe begins to shift. The oldest stars, once considered ancient, become young in comparison to the relic structure. The first atoms, formed minutes after the Big Bang, seem recent in the shadow of something formed billions of years earlier. Inflation, once thought to erase all trace of what came before, now appears less absolute. Nothing in physics forbids structures colder than time itself. Nothing prevents geometry from passing between cosmic epochs like a fossil drifting across the boundary of creation. The universe may be 13.8 billion years old, but the story imprinted upon it might stretch far beyond that number, into realms where time is not measured in years but in cycles of birth and destruction. And so the ancient structure forces cosmologists to rethink everything, to question whether the universe's age is fixed or whether age itself is a misunderstanding, an illusion born from our position inside one cosmic chapter. Perhaps the universe is ancient beyond imagining. Perhaps it is newborn. Perhaps both are true. To understand the structure's geometry and why it should not exist, we must go deeper still into the strange mathematics of the cosmos itself. There are discoveries that challenge our understanding of matter, of energy, of forces, of particles. But this one, this silent, ancient form woven into the sky, challenged something far more fundamental, the geometry of the universe itself. To understand why scientists reacted with disbelief, why some sat for long minutes staring at screens in absolute stillness, you must imagine a shape too perfect to survive the violence that birthed everything. The earliest moments of the universe were unimaginably chaotic densities, so high that space itself churned like boiling water. Any pattern, any structure, any hint of order would have been torn apart in an instant. Then came inflation, a burst of expansion so rapid that even metaphors fail. Space stretched by a factor so enormous that anything not uniform, anything not smooth to cosmic perfection, would have been erased. It would be as impossible as finding a delicate sand mandala, each grain arranged with intention and symmetry in the aftermath of a 1,000-meter tsunami. Yet that is precisely what the ancient structure resembles. Deliberate geometry where there should be none. The first step toward understanding the impossibility is recognizing what inflation is designed to eliminate. During those first fractions of a second, the universe expanded faster than the speed of light, not violating physics, because the stretching of space is not bound by the speed limit of objects moving within space. This expansion flattened space-time, ironing out curvature, erasing anisotropies, smoothing away inhomogeneities. It was an act of cosmic simplification, stripping the early universe of individuality. So when scientists speak of geometry that shouldn't exist, they mean a geometry too intact, too coherent, too resistant to that cosmic smoothing. The structure is not random. It has curvature. It has symmetry. It has a subtle twist. a bending as if molded by a higher dimensional shape. Its presence alone suggests something survived, that violent stretching, something inflation should have obliterated entirely. One of the earliest attempts to make sense of it invoked topological defects. These are exotic, theoretical wrinkles in space-time that might have formed during phase transitions in the early universe. If the universe cooled unevenly, regions could have frozen into different states, leaving behind relics like cosmic strings or domain walls, thin, ultra-dense threads or sheets etched into reality. In theory, such defects might leave circular imprints on the cosmic microwave background. But this structure did not match the signature of strings or walls. Those defects create discontinuities, sharp edges, sudden changes in temperature. This structure was smooth, continuous, almost serene. It resembled not a tear in space-time, but an elegant fold, a geometry with intention. Another attempt framed it as a curvature pocket, a bubble of space-time with a different intrinsic curvature than the rest. Imagine a vast, nearly flat sheet of metal with a single, perfectly rounded indentation pressed into it. The rest of the cosmos is smooth. This one region has been gently curved. Such pockets could form if inflation began unevenly in different areas, leaving behind subtle curvature variations. But the more researchers studied the structure, the more its form contradicted this explanation. Curvature pockets should appear irregular, different in size and shape. They should be statistical accidents, not precise shapes. And they should be incredibly rare. Yet this one was not merely rare, it was unique, and its symmetry was too precise. Then came the most radical suggestion: preserved anisotropy. A region where the universe expanded at a slightly different rate, not enough to distort galaxies, but enough to leave behind a faint, circular anisotropy in the cosmic microwave background. Something like a bruise in space-time. The problem was that anisotropies are delicate. Inflation acts like a cosmic eraser, stretching them until they are imperceptible, diluting them into near uniformity. For an anisotropy to survive inflation, it must be extraordinarily large or extraordinarily old. This one was vast, spanning thousands of light years when projected, but its coherence suggested something even stranger. Its geometry was too perfect for a naturally formed anisotropy. The universe is messy. Natural variations leave jagged edges, irregular curves. This pattern was smooth, gentle, almost intentional. And so scientists returned reluctantly to the data. They reprocessed it, recalibrated instruments, cross-compared maps. But with each pass, the structure grew clearer, more certain, more real. Its presence was undeniable. The impossibility was not just its survival, but its tranquility. The universe's birth was violent, chaotic, raw. Yet here was a region of calm, a shape with the quiet confidence of something that had endured beyond its rightful time. Meditating on the structure is like staring into a pond whose surface has stilled after a storm, only to find a perfect ring of ripples that seem to originate from nowhere. The water is calm, the storm long gone. Yet something persists, something that should not. Scientists found themselves drawn to this shape, not because it revealed answers, but because it held them back, as if the universe were telling a story too slow for human impatience. Observers described the structure as hypnotic, a ripple frozen in time, a whisper etched into the cosmic background. Some described it as a boundary, not a wall, not an edge, but the shadow of a geometry that once existed elsewhere. A ripple formed in a prior state, perhaps in a prior universe, carried through inflation in some protected pocket and deposited gently into our cosmos. Not erased, not stretched beyond recognition, preserved. Others saw in it a hint of higher dimensionality, a projection of a shape from beyond our spatial limits, like the shadow of a four-dimensional object cast upon the surface of our universe. A reminder that our cosmos may not be the complete picture, merely the visible cross-section of a larger, hidden reality. The most unsettling interpretation was also the simplest, that this structure should not exist because our understanding of the universe is incomplete, that inflation is not the eraser we imagined, that cosmic smoothing is not absolute, that remnants of something older, something beyond the Big Bang, may persist in forms we have only just begun to recognize. The structure does not speak, it does not change, it does not demand, it simply is. A silent contradiction, a quiet defiance, a geometry born in a world without atoms, without light, without time as we understand it. And the deeper scientists looked into that geometry, the stranger the implications became, because the structure was not alone. Its existence hinted that the universe may contain entire regions governed by a different history, regions shaped not by our cosmic beginning, but by something that came before. To follow this thread, to unravel the origin of this impossible geometry, we must expand our search beyond space, into time, into memory, into cycles far older than our universe. There is a particular kind of silence that arises only when scientists confront something that does not fit. It is not confusion nor hesitation. It is the void-like quiet of minds brushing against the edge of knowability. This was the silence that settled over cosmology in the months following the announcement. The structure, whatever it was, should not have existed within our universe's permitted borders. And because it existed anyway, the conversation inevitably drifted toward the unthinkable, not toward aliens, not toward engineering, not toward intelligence. Toward time, toward history, older than everything. The idea that our universe is not the first. Even among physicists, the words previous universe are spoken carefully, like a small flame one does not want to extinguish or let burn out of control. And yet, as the data accumulated, more researchers allowed themselves to consider it, not as fantasy, but as a genuine explanatory path. It began with a renewed look at cyclic cosmology, the ancient-sounding notion that the universe expands, slows, collapses, and is reborn in an endless series of cosmic breaths. Modern versions of this idea are far more mathematically sophisticated than the philosophical musings of old civilizations. In some models, the contraction phase creates incredibly high-density conditions that seed the next expansion. In others, the collapse never quite reaches a singularity. Instead, the universe rebounds from a finite minimum, leaving an imprint of its prior state faintly encoded in the early plasma. Under ordinary circumstances, any such echoes would be obliterated by inflation, that violent ballooning of space-time that wiped away almost all structure in the first fraction of a second, like a painter rolling a fresh coat of white across a wall. Inflation erased imperfections, smoothed curvature, and hid prior history. But the structure discovered in the cosmic microwave background did not behave like an imperfection, nor like curvature, nor like anything inflation should have erased. It had geometry, a self-similar signature. Its statistical pattern, though faint, was too organized to be random, too old to be ours, too smooth to be turbulence, too narrow to be an inflation artifact. Something about it felt preserved, as though sealed in amber long before the Big Bang settled into the fireball that would one day birth stars and matter and thought. One of the theories revived by this was Roger Penrose's conformal cyclic cosmology, known for decades but lingering at the fringes of mainstream models. CCC proposed that each aeon of the universe ends in a state where all mass evaporates, leaving only radiation. In that strange, sparse realm, without particles to measure time, the geometry of the universe can be rescaled and treated as the beginning of a new Big Bang. In Penrose's view, the universe is not reborn from collapse, but from dissolution. The end of one aeon bleeds seamlessly into the start of another. When the Planck satellite data first suggested possible low-variance circles in the CMB patterns Penrose argued were remnants of black hole collisions from a previous universe, the idea was debated with mixed enthusiasm. Many dismissed the findings as statistical illusions. Others admitted that the anomalies were real but unrelated to CCC. But in 2025, deeper reanalyses of old data combined with new computational techniques revealed something far stranger, a high-order coherence pattern inside one of those low-variance patches. It was not a perfect match for Penrose's circles, but it belonged to the same family of anomalies, unexpectedly ordered features, neither fully erased nor fully random. And the structure at the center of the controversy was nestled within that very patch, as though some cosmic hand had placed it there millennia before inflation, stars, atoms, or space as we understand it. The question then arose, could something survive an entire cycle? Could information pass from one universe to the next? Cyclic models offered an answer, tentative, fragile, controversial, yet astonishing, yes, under certain conditions. In loop quantum cosmology, for instance, the bounce between universes may preserve a few fragments of quantum geometry. In some versions of ekpyrotic models, the collision between higher dimensional branes that triggers a new Big Bang might also transmit certain boundary configurations. In conformal theories, the universe's final state, stretched across unimaginable timescales, may encode a memory of sorts, a ghostly remnant of immense processes long faded from matter. None of the models predicted something as specific as what was found. They offered frameworks, not answers. But each of them permitted the possibility that the structure did not originate in our universe at all. The notion felt absurd at first, a message, an image, a fossil carried across the death of one cosmos into the birth of another. Not a communication. Communication implies intent, timing, receivers, senders. This was something deeper, more like sedimentation. The way the trace of a prehistoric creature is preserved in stone, not because it was meant to be, but because the universe happened to arrange itself in a way that kept the imprint intact. If another universe had existed before ours, and if it had undergone processes, we cannot imagine it might have left behind patterns imprinted in the fabric of space-time itself. To detect such a pattern would be to glimpse a memory from before everything. Astronomers familiar with the data described the feeling in metaphors, like hearing a faint whisper beneath a roaring waterfall, like seeing a shadow of something that should not cast one, like noticing a symmetry in a horizon that ought to be featureless. It was not loud, it was not clear, but it was there. And beneath the scientific discourse lay a more philosophical disturbance. If echoes exist, what kind of universe leaves them? One where entropy eventually smooths everything into uniform radiation, or one where structures grow so large and so old that even eternity cannot fully dissolve them, or one where intelligence, if it ever arose, learned to manipulate space-time itself and left behind fingerprints, unintentionally or otherwise. The structure did not answer this. It only deepened the enigma. But the 2025 analyses carried another implication, one even more disquieting. The patch containing the anomaly was not isolated. Subtle correlations, weak, elusive, but statistically persistent, hinted at a second feature, far larger and far fainter, on almost opposite sides of the sky. Its geometry was too diffuse to classify, but its orientation seemed linked to the primary structure, as if both were parts of a larger whole that inflation failed to erase equally. Cosmologists struggled to imagine how something so vast could exist before the Big Bang, or why it would have symmetry across regions that should never have been causally connected. These questions led back to the heart of cyclic cosmology. Perhaps causality itself is not a permanent structure, but something reborn with each cosmological iteration. Perhaps the end of one universe and the beginning of another are not separated by fire and violence, but by a seamless transition beyond our comprehension. Whatever the truth was, the discovery forced humanity to confront an unfamiliar sensation, not insignificance, but ancestry. If the structure truly was an echo, then we, not just humans, but stars, galaxies, the laws of physics themselves, were descendants of something older, children of a universe whose last breath still lingers faintly in the cosmic static that fills our sky. And so in the quiet offices of cosmologists, in the observatories beneath high mountain air, in the late-night emails between physicists chasing equations across continents, a new understanding began to grow. Our universe may not be alone. It may not be first. And the traces of what came before may still be speaking softly, subtly, across unimaginable gulfs of time. Not to tell us something, but simply because the universe remembers. Across the history of astronomy, every structure we have ever studied, every nebula, star, dust cloud, quasar, cluster, filament has shared one common ingredient: matter. Even gravitational waves, though not composed of atoms, arise from masses in motion. The cosmos, in our scientific vocabulary, is a story told by particles. But the pattern uncovered in the cosmic microwave background refused to cooperate with that story. It did not behave like matter. It did not bend space the way mass does. It did not emit or absorb light. It had no spectral signature, no temperature deviation that matched any known process of baryons or dark matter. It wasn't a clump, nor a void, nor a filament. It didn't correspond to any map of early plasma or later cosmic evolution. In a very literal sense, it wasn't anything. And yet, it had form, a shape held not by particles, but by the fabric of space-time itself. The first hints came from gravitational lensing data. When researchers tried to reconstruct the local curvature around the anomaly, they found something unsettling. The geometry shifted, subtly but consistently, even though no mass was present to cause the effect. It was as if the space-time metric had been etched with a pattern, one that exerted no gravitational pull, yet still influenced the paths of photons passing through it. The team working on the reconstruction described it as a fossil of curvature. That phrase stuck because nothing more accurate existed. What they were observing was a deformation not sustained by mass energy, but preserved as if space-time itself remembered having been shaped once, long ago, under conditions that no longer exist. This realization led to one of the strangest conclusions in modern cosmology. The structure was not made of matter, radiation, or any known field. It was a relic of geometry alone, a structure without content, a form without substance, a ghost architecture. To understand how deeply this defied expectations, one must consider the timeline of the early universe. Before atoms, before stars, before protons or neutrons, there was the primordial plasma, an opaque fog of electrons, quarks, and radiation. Before that, the symmetries of the universe were so extreme that familiar concepts like matter had not yet differentiated from the energy that saturated space. And before even that, before the first fractions of a second after the Big Bang, lay the pre-inflationary epoch, a regime so compressed and so brief that our physical models barely scratch its surface. In this domain, space-time was dynamic and restless, its geometry fluctuating violently. Any structure present then, no matter how bold, should have been obliterated when inflation began. The expansion was so fierce and so fast that all irregularities, no matter how large, should have been flattened into uniformity. Yet this structure endured. Not perfectly, its edges blurred, its symmetry softened, but it endured enough to be detectable billions of years later, faintly printed across the light released when the universe first became transparent. If it had contained matter, inflation would have smeared it into a thin wash of density. If it had been a topological defect, a cosmic string, a domain wall, a monopole, it would have left a different signature. Discontinuities, abrupt temperature jumps, localized anisotropies. Instead, the anomaly stretched smoothly across space, too subtle for such defects and too persistent for random fluctuation. The only category left was the strangest: pure geometry. Some physicists propose that the structure might be a remnant of quantum gravity, an imprint from the era when space-time itself was an active, fluctuating field of discrete units. In those extreme conditions, geometry behaves less like a static backdrop and more like a frothing sea, its curvature fluctuating according to rules we still lack. Under such a model, the structure could have emerged as a resonant standing pattern, something forged by the deep vibrations of space-time before it cooled into the smooth continuum. We know others argued that this was evidence for pre-geometry, a hypothetical phase where space-time did not yet exist in its familiar form, and where something like a proto-structure set initial conditions later inherited by the Big Bang. Such a relic would be older than the universe, not in a temporal sense. Time did not yet have meaning, but in an ontological one. It would be a trace from the realm before time. And there was a more unsettling interpretation, that the structure belonged to another universe entirely, surviving the transition into ours, not as matter or energy, but as curvature carried forward by continuity of the underlying mathematical space. In that perspective, the anomaly was not something our universe created, it was something our universe inherited. Regardless of the interpretation, the implications remained the same. This was not a thing. It was a shape imprinted on the substrate of space-time, a shape with no atoms, no molecules, no particles, a pattern that could not be touched, detected directly, or interacted with, only inferred by the way it influenced the flight of ancient photons and the angles of distant galaxies. A ghost architecture, surviving like a fossil long after the creature itself had vanished. The more the data were analyzed, the more this picture solidified. There was no mass connected to the structure, no energy over density, no gravitational well. It did not warp space in the classical sense. Instead, it altered the metric in a way that should not be stable, yet somehow was. The curvature behaved like a scar on space-time, not actively maintained, but frozen into place by the universe's earliest conditions. Scientists struggled with the language for this. Some called it a null density artifact. Others preferred metric imprint. A few leaned toward geometric fossil, a term that captured both the ancientness and the strangeness of the phenomenon. But none of these terms conveyed the deeper implication. If geometry can store structure independent of matter, then the early universe was capable of processes far more intricate than standard cosmology predicts. Something before matter, with no building blocks, no atoms, no forces as we know them, managed to produce a pattern organized enough to persist across 13.8 billion years of expansion. That persistence alone was startling. Geometry ought to relax, smooth out, decay, but this one did not, which raised an uncomfortable question. What kind of event or process could carve a structure into space-time so deeply that not even inflation erased it? The researchers did not answer that. They could not. Instead, they continued to map the anomaly, tracing its contours as if exploring the foundations of a building whose stones had long since crumbled away. A building without walls, a relic without matter, a memory without a mind to remember it, a structure that outlived its universe simply by being a shape the cosmos could not quite forget. Long before the first stars burned, before atoms cooled into existence, before even light could move freely across the infant cosmos, one force had already begun its quiet, tireless work. Gravity, ancient beyond measure, older than particles, was already shaping the universe, long before the universe had anything to shape. In that sense, it was the first architect. Not a creator in any mythic sense, but a sculptor whose tools were curvature and time, and whose canvas was the very structure of space-time. For decades, we pictured gravity as a gentle, patient artist, weaving the cosmic web through slow accumulation, drawing galaxies together over billions of years. But the discoveries of the last few years have begun to reveal something far more ambitious. Gravity, in the earliest moments, was not slow. It was wild, almost improvisational, capable of sculpting with an intensity we can scarcely imagine. And it is here, within that frenzied pre-matter epoch, that some cosmologists believe the impossible structure may have originated. Yet even that idea struggles, because the timing does not align with known physics. The structure appears older than any gravitational process should allow. The story begins with the new dark matter maps released in 2025, the culmination of several international surveys combining weak lensing measurements, high-resolution simulations, and data from the latest gravitational wave detectors. These maps revealed something shockingly intricate. Dark matter did not cluster solely in the diffuse filamentary networks we were accustomed to. Instead, in certain regions, the distribution displayed faint, repeating motifs, geometric configurations that echoed the same shape seen imprinted on the cosmic microwave background. They were not perfect matches, not replicas, but they shared a symmetry, a rhythm, as though gravity had been following a blueprint it had inherited from an earlier time. And then Gaia DR4 arrived. The fourth data release of the European Space Agency's Stellar Survey expanded the catalogue of stars, motions, and gravitational interactions to a level of detail never achieved before. When astronomers analyzed subtle movements in distant galactic halos, motions too slight to be caused by visible matter alone, they found that these motions traced invisible contours, faint gravitational boundaries that mapped onto the same strange geometry embedded in the microwave background. It was as though gravity itself remembered the pattern. Gaia's data hinted that the structure was not just a relic frozen in space-time, but something gravity had responded to, embraced, and elaborated upon. Yet this made the mystery deeper, not simpler, because that meant the structure existed early enough for gravity to build upon it, earlier than galaxies, earlier than stars, earlier, perhaps, than the Big Bang's cooling plasma. But the most startling clues came from JWST. As its instruments peered deeper into cosmic history, it found galaxies forming far too early, far too large, and far too structured to fit the timeline we had been using for decades. Some of these galaxies, redshifted to the brink of our observational horizon, appeared to have stellar populations that should have taken hundreds of millions of years to assemble. Yet there they were, already mature, lying along the contours of the very same anomalous geometry. It was impossible, and yet there it was in the data. These galaxies did not appear randomly. They clustered in ways that suggested gravitational guidance, as though the structure had whispered instructions into the early universe, telling matter where to collect, where to drift, where to form the first luminous islands in the dark. This led some researchers to propose that the structure may have acted as a kind of scaffolding, something gravity used as a foundation upon which to build the cosmic web. Not a physical scaffold, not made of atoms or dark matter, but a geometric template, a fossilized pattern older than matter, older than time as we understand it. But if gravity used this template, where did it come from? Some pointed to gravitational wave fossils, hypothetical remnants of the earliest distortions of space-time. These waves would have been produced during primordial processes, perhaps even before inflation. While ordinary gravitational waves decay, losing intensity as they stretch with the expansion of space, certain configurations, if embedded deeply enough, could, in theory, imprint lasting curvature. Not energy, not mass, but shape, a fossil wave. A memory of space-time's earliest oscillations. Others turned to the possibility of primordial black holes, objects that could have formed not from collapsing stars, but from fluctuations in the density of the infant universe itself. If such black holes existed before inflation, and if they evaporated through Hawking radiation or were torn apart in those violent instants, their gravitational signatures might have been stretched smeared and preserved as geometric scaleta across vast scales. A cosmic scaffolding left behind when the black holes themselves were long gone. But even that ran into the same problem. Inflation should have erased the pattern, smoothed it, diluted it, until no trace remained. Yet the structure persisted just enough to be visible in the background radiation and echoed faintly in the large-scale behavior of galaxies. This contradiction has become one of the most uncomfortable puzzles in cosmology. Because if the structure predates inflation, then inflation did not work the way we believed. And if it formed after inflation, then the early universe was not uniform. Either interpretation cracks open our standard model of cosmology at its foundations. As researchers integrated the Gaia-DR 4 motions, the dark matter maps, and JWST's early galaxy anomalies, a larger picture began to emerge. The structure was not a galaxy, not a void, not a topological defect. It was something gravity responded to, like a blueprint, a faint instruction manual etched into the universe from its first moments. But instruction manuals imply intention. Most physicists reject that interpretation. But even without invoking intention, the fact remains: something shaped gravity before gravity shaped the universe. There is, however, one more possibility, one that became prominent in 2025 as new models of quantum gravity and early universe simulation matured. It suggests that this structure is not a consequence of gravity, but the cause of gravity's earliest behavior. That gravity did not sculpt the structure sculpted gravity. In this view, the structure is a relic from a pre-geometric phase, a time when space-time was governed not by curvature, but by a deeper set of rules, unknown, perhaps unknowable, that only later crystallized into gravity as we understand it. When gravity solidified out of that primordial phase, it inherited the structure as its initial condition. Gravity, the ancient artist, was not the architect after all. It was the apprentice, and the blueprint it followed was older than the Big Bang itself. If you stand back far enough, if you step outside the familiar realm of neurons and organisms and the narrow slice of time we call human history, something unsettling begins to take shape. It is the idea that complexity itself is a kind of awareness, that order can emerge anywhere conditions allow, and that what we call consciousness might be only one expression of a deeper cosmic principle. For centuries, the assumption was simple. Consciousness emerges from biology. It requires cells, chemistry, fragile networks of carbon, oxygen, and hydrogen assembled with exquisite precision. A brain, a nervous system, metabolism, life. But as our understanding of complexity theory has expanded, that assumption has begun to erode. Nature produces organization across every scale, in the spirals of hurricanes, in the branching of rivers, in the structure of galaxies, in the quantum algorithms of particle interactions. Complexity is not a rarity. It is the universe's default behavior when energy, time, and freedom are available. And so a question appears quietly, cautiously, like a shadow moving just outside the circle of firelight. What if the universe itself organizes in ways that mimic the processes we associate with thought? What if consciousness, or something adjacent to it, is not tied to biology at all? No one is suggesting an intelligence in the familiar sense. Not a mind, not a presence with desires, memories, or intentions. This idea is far more subtle and vastly more strange. It is the possibility that structure, at its most fundamental, behaves like a computation, not digital, not symbolic, but geometric, a computation of shape, order, and evolution. A computation the universe performs simply by existing. The impossible structure discovered in the cosmic microwave background forced cosmologists to confront this directly. It was a pattern that preceded stars, atoms, even the first flickers of light. A pattern that had no matter, no energy, no mass to anchor it. So what was left? Only geometry. Pure, self-organizing geometry. A shape that had persisted across the entire life of the cosmos. The more physicists studied it, the more it resembled something we see across complex systems. Spontaneous order emerging from chaotic beginnings. Like the way ant colonies optimize paths without a leader. Like how neural networks find patterns without explicit instruction. Like how snowflakes crystallize into intricate designs that no single molecule decides. Complexity does not require intent, it requires only rules. And in the first instant after the Big Bang, if time even existed in that moment, those rules may have been playing out on a scale beyond imagination. Some models of quantum gravity propose that space-time emerges through interactions of pre-geometric units, tiny, vibrating relationships that exist before length, width, or duration have meaning. In these conditions, structure is not content. Structure is action, behavior, a self-organizing process. The anomaly appears to be exactly that. The fossil of a process that organized itself before atoms were available to fill it, a form not built from matter, but carved from the logic of the early universe, a form that gravity later obeyed, not out of intention, but out of necessity. This is where the philosophical turn becomes unavoidable. The discovery forced researchers across physics, information theory, and complexity science to ask a question few were comfortable speaking aloud. Can a pattern be a kind of proto-mind? Not a sentient mind, not a thinking being, but an emergent process that shapes its own environment, reacts to constraints, adapts, and persists. After all, on Earth, consciousness emerges precisely from such a process. Billions of neurons self-organize into a collective that perceives, responds, and remembers. None of the individual neurons knows anything. They simply follow rules. Yet together, they create the phenomenon we call awareness. If geometry can self-organize at the cosmic scale, if the early universe allowed structures to evolve before matter existed, then the boundary between physical pattern and emergent intelligence begins to blur. The structure in the CMB is not alive. It does not think, but it may have arisen from the same deep principle that later allowed life and thought to exist. Complexity first, biology later. One of the radicals in this new wave of theoretical work proposed that the universe computes its own evolution, not metaphorically, literally. The interaction of fields and geometry forms a kind of natural algorithm, one that produces stable configurations, amplifies order, and prunes chaos. In this framework, the early universe was a vast computational phase transition, and the structure we observed was one of the earliest outputs, a stable solution in a sea of unstable ones. Another idea, softer but equally profound, draws from emergence. Some systems produce patterns simply because the rules demand it. When energy flows through matter, vortices form. When sand collapses, fractals appear. When space-time cools from its primordial turbulence, certain shapes may stabilize. But this structure was too specific, too persistent, too organized to dismiss as a random fluctuation. And so some physicists began to wonder whether the universe had gone through a kind of pre-biological self-organization, an era when complexity flourished, when geometry was alive with patterns, before particles locked the universe into the simpler behavior we see today. The most provocative question was whispered in conferences, written in footnotes, debated in the corners of research groups. Could this structure represent the earliest form of what we might call proto-information, a precursor to the processes that would one day allow minds to exist? Not intelligence, but the seed of intelligibility. If so, then consciousness may not be a rare chemical accident, but a late expression of something woven into the universe from its beginning. The tendency of reality to organize itself into structure, to preserve patterns, to build complexity from simplicity. The structure in the CMB would then be the oldest surviving example of this cosmic impulse, a pre-matter manifestation of the same principle that billions of years later would ignite inside neurons and produce thoughts. Not a message, not a memory, not a mind, but a hint that the universe has always been capable of more than chaos. That order is not the exception, it is the rule. And if order can arise before matter, if geometry can self-organize before atoms exist, then perhaps consciousness, in its broadest definition, is not tied to biology at all. Perhaps consciousness is what happens whenever the universe becomes capable of noticing itself, even if the noticing is nothing more than a pattern that refuses to disappear. And in that sense, the ancient structure is not an artifact of intelligence. It is the ancestor of it. It began as a rumor inside a subfolder of a subfolder on a European Space Agency server, an internal note, unsigned, almost embarrassed to exist. A single line, lensing anchor point appears shifted by 0.03 arc seconds, drift unexplained. At the time, it was the kind of anomaly mission leads like to bury until they're sure it's real. It smelled like calibration error, or a misaligned reference star, or someone forgetting to account for an instrumental thermal cycle. But then the same shift showed up in a Japanese group's reanalysis of Subaru HSC survey data, and again in a Chilean team's deep lensing mosaics from the Rubin LSST Pathfinder. And finally, more dramatically, in JWST's 2025 ultra-long baseline gravitational lens monitoring campaign, arcs that were once razor-stable began to show faint but measurable distortions over multi-year comparisons. Not noise, not a glitch. Something vast was moving. At first, the shift was interpreted as a local effect. Perhaps we were misunderstanding the distribution of dark matter in a given cluster. Perhaps subhalos were repositioning or evaporating. Perhaps a primordial black hole population, once dismissed, was slightly more dynamic than assumed. But this explanation unraveled when the anomalies began appearing in regions that shared no common structure, no overlapping cluster, no traceable mass. Each drift implied a deviation in gravitational potential across distances, so enormous they laughed at the idea of any conventional object causing them. The uncomfortable proposal emerged from the increasingly frantic cross-team workshops in early 2025. We are not watching matter move. We are watching space-time itself, its density scaffold, its hidden architecture shift, slowly, methodically, like a glacier. The shift was tiny from our human perspective, a fraction of an arc second in lensing curvature here, a few parts per trillion deviation in cosmic shear there. But scaled up to galactic distances, these distortions were monumental, on the order of billions of solar masses worth of gravitational influence, subtly reconfiguring its form. The ghost architecture, first theorized in the earlier chapters, was supposed to be static, a fossil from before the universe cooled, a leftover lattice from inflation's chaotic freeze, a relic, beautiful and inert. But relics don't move, and so the scientific narrative had to pivot painfully, reluctantly, towards something that had once been unthinkable. The universe's underlying geometric framework might not be dead. It might be evolving. The first major evidence came from the JWST Frontier Lens Drift Report, released in April 2025 after months of internal argument. It documented an ultra-stable lensing system, a quasar split into 4 perfect Einstein images used for precision cosmology. These images had been unchanged for as long as modern instrumentation had watched them. But JWST's latest high-resolution temporal grid showed that one of the arcs had shifted by a measurable micro-distortion, a slight elongation, as if tugged by an invisible finger. This deformation wasn't consistent with dark matter substructure movement, nor with a passing mass, nor with instrumental changes JWST's teams checked, rechecked, and re-rechecked. The same distortion appeared in parallel observations from other telescopes. More alarming, the distortion had directionality. It wasn't random. It aligned with a faint anisotropy detected in the cosmic expansion field, a drift noted in late 2024 but dismissed at the time. Independently, Gaia DR4's astrometric anomalies, stars drifting in tiny, unmodeled ways, were beginning to point toward the same cosmic direction. Across multiple datasets, spread across years, platforms and instruments, the signature was consistent. A reconfiguration of space-time density was occurring. If this structure was truly a fossil of pre-matter geometry, a framework etched into the universe when it was still a boiling quantum foam, its movement posed profound questions. Why would a primordial lattice shift? Did inflation freeze in a pattern that was still capable of evolving? Was the ghost architecture responding to expansion differently than ordinary matter? Or, and this was the most disturbing proposal, was the universe's shape not fixed but dynamic? Were we witnessing the slow rearrangement of the cosmic web's foundation, not its matter but its blueprint? Picture the universe's structure as a colossal three-dimensional spiderweb laid down before atoms existed, a geometry carved by quantum fluctuations amplified to cosmic size. For 13.8 billion years, we assumed the web stayed still, while matter flowed through it. But what if the web itself flows? Not rapidly, not violently, but in a deep, tidal, glacial crawl, one that only becomes apparent over billions of years, now just barely teased out by 21st century precision instruments. One explanation gaining traction in 25 was the geometric glacier model. Early space-time may have crystallized into a quasi-stable pattern, like a cosmic solid. Over cosmic timescales, this solid geometry could undergo restructuring, a slow relaxation toward lower energy configurations. This isn't matter rearranging. This is space-time relaxing. This model borrowed from condensed matter physics. Defects in crystals migrate, stresses propagate, and dislocations shift over time. What if inflation left behind something similar? A cosmic macrocrystal whose imperfections resolve themselves across epochs. Gravitational lens drift, cosmic shear distortion, Gaia astrometric offsets, expansion anisotropies. None individually proved anything, but together they painted a picture. The structure was not a fossil. It was a living geometry, still settling into its shape long after matter, galaxies, and life emerged around it. And then came the final, most haunting piece of data, the 2025 multi-frequency CMB lensing reanalysis. Using updated algorithms, researchers discovered tiny but coherent changes in the gravitational lensing of the cosmic microwave background compared to reconstructions from the early 2010 seconds. This meant one thing: the structure had moved, relative to us, between now and a decade ago. Not much, but enough to measure, enough to disturb, enough to imply that the cosmos is not a static stage upon which matter performs, but an active participant, a shifting foundation, a slow dancer whose steps we only now notice. By mid-2025, a new consensus was emerging, not officially, not publicly, but whispered in late-night Zoom calls and private Slack channels. The universe is still building itself. Its oldest architecture is in motion. And we, fragile specks that we are only now learning that the ground beneath existence, the geometry we assumed permanent, is drifting, rearranging, evolving. The structure moves. The universe is patient. It moves in rhythms so slow that human perception can barely grasp them, and yet, over billions of years, the cosmos undergoes transformations, both subtle and profound. The ancient structure, drifting imperceptibly through the folds of space-time, will one day intersect the path of our galaxy. It is not a collision. It is not a catastrophe. It is an encounter of a very different kind, one that will stretch our understanding of what it means to inhabit a universe with memory and geometry older than matter itself. As the Milky Way sails through the vast cosmic expanse, carried by its own momentum and the gentle tug of gravitational neighbors, it will gradually drift into a region influenced by the structure. On human timescales, nothing will appear to change. Stars will orbit their galactic centers as before, comets will trace familiar arcs, and planets will continue their silent revolutions around their suns. But over millions and then billions of years, the imprint of the structure will begin to assert itself, not violently, but in ways that alter the subtle rules of physics in our neighborhood. Time itself, the seemingly constant river in which all events unfold, will behave differently. The structure carries with it a minute, yet measurable, deviation in space-time curvature. Clocks, light paths, and even the decay rates of subatomic particles could be affected ever so slightly. The effect is not catastrophic, but cumulative. Millisecond pulsars, the cosmic timekeepers of the galaxy, may begin to drift from predicted periods. Gravitational waves propagating through this subtly altered space-time might carry distortions that future astronomers will eventually detect. For any civilization with instruments sensitive enough, these differences will reveal a universe that is older, more intricate, and more responsive than previously imagined. Alongside these temporal shifts, the structure's influence on spatial geometry will create anomalies in curvature. Light will bend along subtly new paths. Gravitational lensing will no longer correspond precisely to mass distributions as previously mapped. The cosmic web, the sprawling network of filaments and voids, may experience slight reorganizations as the underlying geometric scaffold evolves. Galaxies will drift imperceptibly along these gradients, their motion guided not by conventional gravitational attractors alone, but by the ancient contours of a pre-matter universe. Observers in this distant epoch may witness arcs of starlight bending in ways that defy simple explanation, perceiving a cosmos whose shape carries the whisper of its own deep history. The effect on star formation will be equally subtle but no less profound. Molecular clouds, the cradles of stellar birth, respond to gravity, pressure, and local curvature. As our galaxy enters the region shaped by the structure, these clouds may collapse differently, forming stars at slightly altered rates. Spiral arms may shift in density patterns. The distribution of supernovae may take on new asymmetries. Over hundreds of millions of years, these small deviations could lead to a galaxy that looks familiar in broad outline but subtly different in detail. A Milky Way reshaped by a force that is neither visible nor material, but geometric and ancestral. The encounter will be a gentle one, a slow immersion into a region of space-time older than stars, older than atoms, older than the very concept of matter. It is not an arrival into chaos, but into a different rhythm, a place where the universe's original geometry begins to assert itself once more. For future observers, the night sky will contain hints of this underlying pattern, lensing distortions, unexpected stellar motions, anomalies in galactic rotation curves. These clues will reveal a cosmos in motion not merely through space, but through its own ancient shape, a universe that is still learning how to unfold. From a philosophical perspective, this meeting with the structure is humbling. It demonstrates that the universe is not a static stage upon which matter acts, but a living framework whose architecture predates everything we recognize as tangible. The Milky Way, our solar system, the planets, and even the atoms that compose life will all drift into a region where space-time itself carries memory, where geometry preserves the echoes of events long before matter emerged. Life and intelligence, if they still exist in some form, will experience a cosmos that is subtly different, shaped not only by the forces we know, but by the legacy of a structure older than any star. The encounter underscores the interplay between scale and time. Human civilization perceives the universe over decades, centuries, at most millennia. Yet the cosmos operates over billions of years. Events that seem static to us, galaxies frozen in their positions, clusters unmoving, voids vast and empty, are in truth part of a slow, flowing process. The structure moves at a pace almost imperceptible, yet inexorable. Our descendants, looking back at the motions of stars and galaxies, may see hints of a hidden choreography, one that began long before the first humans watched the night sky, and that will continue long after we are gone. In this future, the universe does not crash into us. It does not shatter or tear. Instead, it invites us into a new understanding of reality, where physics is subtly malleable, where time and curvature are not uniform, and where the legacy of primordial processes continues to shape matter, light, and energy. It is a future defined not by destruction, but by revelation, a slow unveiling of the deeper rules and hidden memories embedded in the cosmos. The encounter also reinforces the notion that the universe's story is ongoing. It began with quantum fluctuations, inflation, and the first atoms, continued through the formation of stars, galaxies, and life, and now moves inexorably toward interactions with structures predating matter itself. The Milky Way's journey into the region of the ghost architecture is a continuation of that narrative, a reminder that cosmic evolution is not just the passage of time, but the unfolding of geometry, memory, and emergent order on scales we are only beginning to measure. And as the timeline stretches forward, billions of years into a distant future, we begin to appreciate the vastness of possibility. The universe will continue to expand, stars will live and die, galaxies will collide, and the structure will remain a witness to all that has passed, gently reshaping the framework through which matter moves. It will not dominate, it will not destroy. It will simply exist, subtly influencing the universe, offering a chance for comprehension to civilizations patient enough and observant enough to notice, to stand within that future Milky Way, to look up at the stars influenced by a pre-matter geometry, is to witness the universe's memory in action. It is to realize that the cosmos is not merely a collection of particles, forces, and fields, but a living history encoded in the fabric of space-time itself. When our galaxy enters this region, billions of years from now, the universe will be offering its oldest story in a language of curvature, light, and time, an invitation to perceive its memory long after the first stars burned out and the first civilizations vanished. It is a future defined not by fear, but by awe. A slow, patient revelation of the deep architecture of existence. The Milky Way, carrying countless stars and the potential for life yet to evolve, will drift into a region where physics subtly changes, where geometry whispers of the universe before matter, and where the cosmos itself can be felt as a persistent, evolving memory. In this encounter, the universe will show that even in its immense age and scale, it is not indifferent. It is remembering, and we, or whatever succeeds us, will be there to witness it.